Hey guys, it's Servo Robotics here. Today I'm going to be unboxing, setting up, and reviewing the myCobot 280 Raspberry Pi. It's about an $800 arm. It has a 280 millimeter reach, 6 degrees of freedom, weighs about 860 grams, and has a 250 gram payload. So it's pretty compact and honestly really good for research. I bought it for my graduate project and it has not disappointed so far. So to start with, we have the product certification. It's stamped quality checked, which is nice to see on an $800 robot, just knowing that it's actually been checked before shipping. It also comes with a user manual. I didn't use it too much though. The setup for this arm is very simple and intuitive, and you can basically get it functioning right out of the box. Slight emphasis. Here's the box the arm came in. I personally thought it looked pretty good. It was a nice touch to see some decent packaging, and shipping was also super fast. I think I got it within a week, which was cool. Here's the flat base. It's got those little holes in it for these tiny Lego style screws that come with it. And here's how the feet for the base set up. Here are the DuPont jumper wires. These are basically breadboard style cables for connecting the onboard Pi or expansion ports to sensors and small prototype circuits. And then we've also got the Lego style screws that are used pretty much everywhere on this robot. So I'm just fitting the screws in here. We have the same holes at the bottom of the base, and you just plug those in. So it's a pretty intuitive setup. Here's the adaptive gripper. This also comes in a nice little box, and inside it has small servos fitted into the mechanism, so the fingers are actively driven instead of just being spring-loaded. That means the gripper can open and close under motor control, which makes it much more useful for basic pick-and-place tasks. We've got the same holes at the end effector and on the gripper for the same Lego-style screws. So I'm just going to attach the gripper here. Then I connect the 3-pin signal cable for communication with the gripper, and they've put a nice extension interface on the end effector, which makes it pretty easy to connect accessories. The only small problem I've had is that the flat base is too light compared to the arm. The Lego system works great for the gripper, but for the base I would have gone for the G-shaped base that clamps onto a desk if I could pick again. Here's the power cable. It's a 12-volt DC adapter, and I'm plugging the barrel connector into the power input on the base. It also comes with a standard US Type A plug, and that worked perfectly with no issues. Once it's plugged in, all the LEDs at the back of the end effector go green, and the joints become fixed. From there, the arm is controlled through the Pi. They provided a micro HDMI cable, so I connected that to my monitor and then used the USB-A ports on the base to connect my keyboard and mouse. The Pi has pymycobot installed out of the box, along with a nice educational block interface made by Elephant Robotics. Once it's connected to the internet, the arm is ready to go. After connecting the onboard PI to the internet, I connected to it using SSH. Then I wrote a small Python script using pymycobot to move the robot and the gripper. Used nano to save the code into a file called run_demo.py and saved it into my home directory on the Pi. Then it was just a matter of executing the code. As we can see, the arm goes into position and the gripper opens and closes. And then finally, I wanted to show the gazebo integration part. And this is the part that actually impressed me the most. What I'm doing here is running MoveIt and Gazebo on my laptop because realistically, the Raspberry Pi inside the robot is not the machine you want doing full simulation and motion planning. So the laptop handles the heavy side, it plans the trajectory, Gazebo executes it in simulation, and my ROS 2 bridge subscribes to the ARM controller state while that motion is happening. That topic is publishing the commanded joint positions at around 30 Hz. Once the Gazebo motion finishes, and there are no new changes for about 2 seconds, the bridge sends the full trajectory buffer over Wi-Fi to a small server running on the Raspberry Pi. The Pi downsamples that full trajectory into about 15 key waypoints, and pymycobot impressively fills in the blanks. And the next step is replacing the Gazebo camera topics and simulated point clouds with point clouds from my actual 3D depth camera. Once that's done, this becomes a full, real-world pick-and-place pipeline, where the robot can perceive objects in a physical workspace, plan the motion, and execute it on the real arm. I'm also going to be open sourcing the full pipeline, so anyone with a myCobot and a depth camera can get set up quickly and run real-world pick-and-place without having to build the whole stack from scratch. Overall, I've been pretty happy with the myCobot. It's small, easy to set up, and pretty good for research and education. The base could be more stable, but apart from that, it's been a really nice platform to work with. So yeah, that's the unboxing, setup, and first test of the myCobot. 280 Pi. I'll be doing more with Gazebo, ROS, and motion planning in future videos.